finally, I'd like to return to conservation of energy now to really look at gravitational potential energy and kinetic energy together. Now, the book introduces this idea of the energy bar chart. I think this is okay, but there's going to be later energy diagrams that I think are even better. The idea of the energy bar chart is that our two energies that we're dealing with in this situation, kinetic and gravitational potential, remain constant. So as kinetic decreases, we see that the gravitational potential energy must increase. Where kinetic is zero, our gravitational potential energy is maximal and equal to what our initial value was. So in this case, we're imagining the situation of a ball that starts at ground. So initially its gravitational potential energy is zero because it starts at y equals zero, and it's launched with some initial some initial speed upwards. Now you know that it's going to slow down as it travels upwards, and by the time it reaches the top point corresponds to a speed of zero. It then turns around and comes back down. So that looks like kinetic energy becoming potential energy, being transformed. At the top, it's all potential energy, then it gets transformed back into kinetic energy, and at the bottom it's going the same speed but in the opposite direction. So this is the idea of conservation of energy when the only types of energy we need to worry about are kinetic and gravitational potential. So this is a scenario that you already know how to calculate with accelerations and velocities, but now this is how you would actually calculate it or deal with it conceptually with energy. So please keep in mind that what we're saying here is that the sum of these two energies are always the same. In this scenario where we don't have any external forces to worry about, if we wanted to think about air resistance, that would be challenging, so we're calling that negligible here, that we get to say that the change in system energy is zero. We see all of the energy, we have nothing external acting on this. We have the ball, and the rest of the system is the Earth to have gravitational energy. So the change in system energy is zero, which means when we add up the changes in kinetic and the changes in potential, that's equal to zero. As we see a decrease in kinetic, our potential has increased such that they sum to zero. Let's now expand our energy model a little bit to include thermal energy. And thermal energy we met in chapter 9, and ideally is coming from something like friction. So the idea being that friction warmed up the surface and took some of our macroscopic energy and turned it into microscopic energy that now we can't actually get back. So it's important to remember when we talk about mechanical energy, we're talking about kinetic and potential energy, and thermal energy is still an energy in our system, but not mechanical. The other thing to remember is that when we had thermal energy, we always talk about a change in thermal energy because all of our surfaces still have some thermal energy to begin with. We don't actually know the absolute value, but we can see how much we've changed it by multiplying the force of friction, which if it's moving with respect to the surface must be kinetic friction, by the length, and I'm going to use L for this, that it's moved. So this is one phrase of this, and again we're talking about an isolated system, and that means that we have no external work done. The change in system energy is equal to zero. Now I can rephrase this equation into the one below it. These two equations are identical. And we get there by remembering that change, delta, is final minus initial. So if I expand kinetic and potential energies to be final minus initial, I then would move the initial to the other side where there is zero. Now again, we only ever talk about a change here, so I leave that with the final energy. So another way of writing this equation that I think is more helpful is that you have some kinetic energy initially in your system, some potential energy initially in your system, and then that becomes transformed in the end to a final kinetic energy, a final potential energy, and a change in thermal energy. So your thermal energy goes on your final side. And again, this is always going to be positive when it's written in this way. So be careful about that you don't make this negative. You can't turn thermal energy into mechanical energy. Now, later on, we're going to talk about what changes here if we have an external force such that we have work, but right now, this is what we need to deal with. Part of why I like dealing with potential energy and not dealing with work is I think it's much easier to get the signs right on potential energy than it is with work.